then also on the Zulip chat that we have. So now you should be able to share. We can see half. No, yeah.
Yeah. Yeah, I haven't made it full screen yet.
Okay, yeah. So our last speaker is Aleks Kissinger. We are going to be composing Hypergraphs, proving stuff with Chyp. Thank you, Aleks.
Hi, so thanks. So I've got just a few slides here, just to give you an idea of what some of the theory is behind this tool, and then I'm going to jump into Chyp, which is a proof assistant for symmetric monoidal categories. Okay, so string diagrams are cool. I think I'm probably preaching to the choir here at applied category theory. So they're sort of the native language for symmetric monoidal categories. They let you put things in sequence and in parallel. And what's even cooler than string diagrams is rewriting string diagrams. So that's where we have some kind of algebraic theory of diagrams. We have some local rules and we apply them to prove stuff. And examples are ZX calculus, graphical linear algebra, et cetera, et cetera, et cetera. So this is great. We'd like to be able to do this kind of stuff in a proof assistant. So the question is, how do we formalize this? One thing you could do is try to use term rewriting. So this is really where I'm just doing plain old term rewriting and treating all of these things as syntax. And actually, when I do a graphical substitution, I'm just turning one term into another term. So this sort of works. But one of the great things about string diagrams is that only connectivity matters, right? So the only relevant data for describing this morphism is what boxes are connected to what boxes. Unfortunately, if you try to do this in syntax, this is what only connectivity matters looks like, right? It's all of the symmetric monoidal category axioms. So if I wanted to do rewriting purely in syntax, then I have to always be doing rewriting modulo all these rules. And that's it's just a pain as a human, but also it's computationally very difficult. It's very difficult to judge if your rewriting system is well behaved, anything like this. So a solution is actually to represent these graphical things as graphical things. And one way you can do that is to represent string diagrams as cospans of hypergraphs. Okay, so here we have a string diagram, and here we have the cospan of hypergraphs it represents. So here, these little blobs are actually hyper edges. Okay, so they have a list of source vertices and a list of target vertices. And then the cospan part is what captures the fact that this thing has a boundary. Okay, so these points here are embedding the input into this hypergraph, and these things here are embedding the output. And this lets us nicely do composition as a combinatoric operation on these things. So I can just push out pairs of these hypergraphs to get the normal way that I would compose string diagrams. And I can also stack them to get the normal way I would take tensor products. Okay, and the benefit of this is that all of these symmetric monoidal category axioms are just completely swallowed by hypergraph isomorphism. Okay, so it kind of, this representation does all this work for you. Okay, and there's a whole theory of this stuff, which me and Filippo Banchi, Fabio Guiducci, Pavel Sobocinski, and Fabio Zanazzi developed in the course of these 3 papers called string diagram rewrite theory. Okay, so what does that mean to you? This is what's going on under the hood. You can really just think about these being this giving us a nice tool for string diagrams. Okay, so Chyp is a tool which does rewriting for symmetric monoidal categories without the bureaucracy. Okay, so there's the tool. I can put the link up again at the end. Okay, so let's actually see what this thing looks like and how to use it. Okay, so I apologize for folks if the text is a little bit small, but well, this is what we have. Okay, so here's Chyp. The way that it works is I type in the bottom and I get pictures in the top. Okay, so let me just start typing gen. The gen keyword says make me a new generator. Okay, I'm going to call it F, and let's say it has 1 input and 1 output. Okay, so you notice as soon as I type that, I see F. Okay, and now maybe I want to put F side by side with itself, I can use the let keyword that says let this thing called h be defined by the following term of f side by side with itself. Okay. Now suppose I have another thing. Oh, let's call it g. Maybe it goes 2 to 1. And now I have f composed with itself, and then I put a g afterwards. And then you can see as soon as I have something that parses, then I get a picture of it. Okay, and I can sort of jump up and down to see what I've done so far. And another thing that's really useful here, so that you don't have brackets all over the place, is to know that the star binds more tightly than the semicolon. So I can always write sort of things layer by layer, okay, and get a nice string diagram. Okay. Now, the way that you do proofs in Chyp is via the rewrite keyword. Okay, and rewrite, it takes a name for the lemma that I'm going to build. Okay, so I haven't actually assumed any rules yet, but let me go ahead and try to prove a trivial lemma. So let me call this thing, well, maybe lim1. Okay, and what could I prove? Well, I could prove something like, I don't know, let me make my life a little easier here and go, g now goes from 1 to 1. Let me prove f g gf equals fg gf. Okay, and you notice that it turns green. Okay, because that's just already true. And this is something that's kind of vacuously true because the diagrams are the same. So remember how I said that isomorphism of these hypergraphs, and notice these things really are hypergraphs up here. Isomorphisms of these hypergraphs subsume all the SMC axioms. So if I did anything else, like maybe if I wrote something like this, then of course Chyp already knows that it's true. Okay, there's also, if I do a rewrite step, I can always justify it using the by statement. But if I drop the by statement, this is always by reflexivity. Okay, so if you recognize this, if you use calc or something like that, then you see this refl command all the time. It just means that these two things are actually equal to each other by reflexivity of equals. Okay, so that's kind of the very basic stuff, but we don't have any rules around yet. So let me start to do something more interesting and build a monoid. Okay, so let me go ahead and save this. Okay. Okay, I'll call you monoid. Sorry, the screen sharing thing is a bit in my way here. Okay, so what is a monoid? It's a multiplication and a unit. Generators, okay? And then it satisfies some rules, okay? So it satisfies associativity, which looks like this, right? And you notice again, as soon as I get something that parses reasonably, I get a picture of it. It should also satisfy a couple of unit laws. So it has a unit on the left kind of rule, which says, yeah, if I plug in a u on the left, I get identity. It has a unit on the right kind of rule. Like so, and that's it, right? So here's my 3 monoid laws. Okay, and once I have this, I can start to prove things based on these rules, okay? And of course, it's very easy to prove things in monoids because this is actually a confluent rewrite system. So actually, I can always just reduce to some sort of normal form to prove that any two equal expressions are the same. So let me just make some lemma again, say lemma 1. And let's, what's a kind of interesting thing to write? Well, how about Just something kind of trivial. If I have something like this, if I plug in 2 units into m, then that should equal u. Okay, now you notice that it's turned red. That says I don't know why that's true yet. But if I say by unit L, then it will know that it's true. And you can see upstairs that it's even highlighted the match that it's used. And here, of course, there's 2 different ways I could have proved this using unit L or unit R, and you can see a different thing highlighted depending on what I do. Okay, so there's a couple of tactics, useful tactics to use in Chyp. The one I've used here is just called rule. Okay, so if I just give you the name of a rule, that's a shorthand for writing use the rule tactic, like so. The other useful tactic is called simp, which just takes a list of rules and it simplifies the left-hand side, the right-hand side, and if they simplify to the same thing, then it will accept it. Okay, so let me write something a bit more tricky. Let's say if I have something like this, let's see, how many inputs does that have? I guess that should be something like this. My types don't check. Any of my locals see what's going on?
Shouldn't it just be equals m?
Equals m because I have 2 inputs. Yeah. Okay, maybe I've made this too easy. Now I have 4 inputs. Let me go something like this. Okay, now you can see I've got a left associated tree of m's and a different kind of tree of m's. Now if I say by a soak, well, that's not enough, but I think if I do by simp a soak, then it's just going to keep applying the associativity rule to both sides until both are reduced to a right associated tree, I believe, and then it will be done. Okay, so this is a case where I've fully typed out the term on both sides of the equation, but actually this is not always so convenient. Sometimes a more useful thing is I don't know what I want yet, but I can just give a tactic name, so something like this, and I hit Control N, and it will find the first match. Well, it'll just apply that tactic, and it will give me what comes out. So now it's applied my tactic to the left-hand side and given me the result. Okay, so I can do it like this to get it in a single step, or I can just say by a soak, do Control N, and then I can also do Control Shift Enter. Oh no, it's already done after 1 step of a soak. Should I try and make this a little harder? Let's say okay, now if I do this, then yeah. Here I can keep applying it. Anyway, I think you get the idea there. So monoids are pretty boring. Let's do something more interesting. Okay, so we have a monoid here. Let's go ahead and add a comonoid to the mix. Okay, so before I had m and u, let me call this n, which goes from 1 to 2, and v, which goes from 1 to 0. Okay, so this is a co-multiply co-unit. And let's add some rules. So co-soak says in times id equals in id times n. Okay, co-associativity. Co-unit on the left should be this, and co-unit on the right should be this. Okay, and of course I could carry on doing exactly the same stuff I did for monoids. Let me save that as comonoid, and everything would just be in reverse. But now that I have these two theories, I can actually import these in a new theory and start to build on top of that. So let me make a new kind of theory, and if anybody knows me at all, they know that the next theory I'm going to make is a Frobenius algebra. Okay, so let me say import monoid. Okay, and the thing that's going to happen then is, well, now I have all the generators of monoid in my namespace. I've also got the rules of monoid in my namespace. Okay, and I'll also import comonoid. Okay, so now I have both of these things around, and you know, I also have the rules from comonoids. This show thing is just showing me a rule. Okay. And now I want to make this monoid and comonoid into a Frobenius algebra. Okay, so I just need to add one more rule. Okay, and let me call it Fra. Okay, and there's many ways you can define a Frobenius algebra. Here's one that I think is nice, which is if I have a co-multiply on the left followed by a multiply on the right, then they can actually sort of trade places horizontally like this. Okay, so here a comonoid here connected to a monoid here is the same as a comonoid here connected to a monoid here. Okay, and now you might not think that this is such a familiar picture of a Frobenius algebra. You're probably used to how this thing on the left turns into a multiply followed by a co-multiply. But then we can actually prove that. So let me prove that. So let's see, how do we do this? Well, let's start with the left-hand side here. Oops, I don't want rule, I want rewrite because I'm doing a proof. And now the first thing I want to do is use a unit law backwards. Okay, so let me unfold a unit on the left, and now I hit Control-N to find the next matching. Okay, well, that wasn't the matching that I wanted. I actually want to unfold it up here on this top wire. So I'll hit Control-N again. Not what I wanted. I'll hit Control-N again. Nope. There it is. Okay, so this was the rule that I wanted. Now I can use my fra rule. I think I want to use it backwards. Well, let's see. We'll see what happens. So I used it backwards here. Put you down there. Okay, so now it doesn't necessarily look like I've made progress, but I'm going to persevere. You can see that I've got what looks like the left-hand side of an associativity here. Okay, so let me do that. Okay, and now it looks like I have a place that I can use my fra rule again. Is it forward? Yeah. And now if I use my unit like so, then I get there. Okay. Woo! Yeah. Now I think, let's see. So now that I've done this, I can make myself look clever to future generations by removing some of these proof steps. Okay, so for instance, if I cut out this step, well, now this is turned red, but if I say simp unit L and fra, it turns green again. Okay, that's cool. I think I can even cut out this step and say simp unit L fra and also. Nope, doesn't like it. So yeah, there we go. So here you notice that the order of these rules matters because I'm working with a set of rules which are not confluent. Okay, so this is the real difference in doing interactive theorem proving versus automated theorem proving is you can handle things which aren't confluent. Just have to be a bit careful with when you apply rules. Okay, so that got one version of a familiar Frobenius law. Okay, so that's Frobenius on the left. I can also do Frobenius on the right. Okay, so let me do that. And that's if I take the right-hand side of this rule up here. And that should also equal m after n. But now this should be simpler. Let's see. By simp for L. Yeah. Okay. So by the time I prove it one way, I can prove it the other way pretty easily. Okay. So that's a Frobenius algebra. I can show some other cool stuff about Frobenius algebras and some of their derived generators. Okay, so one thing I could do is I could say let cup equal unit followed by copy. Let cap equal multiply followed by co-unit. Okay, and now using the Frobenius laws, I should be able to prove the yanking equations. Okay, so rewrite yank L cup times ID, ID times cap. Well, now if I apply the Frobenius law, then I'm here, and then if I use my unit laws, then I will definitely get to the identity. So let me just add them to a simp here. I think I want unit on the left, and I want co-unit on the right. Nope. For some reason we didn't get all the way there. What's going on over here? Oh, I think I know what's going on. What?
It's coordinate, is it right for it? Like the coordinate, right? And
It should be N and B, shouldn't it?
so it's not defined, coordinate, right?
Oh, co-unit R is not defined.
If you go back to the co-monoid,
Do I have a typo? Ah, connuit. Connuit. Ah, this is what happens when you do things live. This is actually very useful. I've got a room full of debuggers here with me. Okay, so now we have yank on the left. Okay, but so this is good. But one thing you start to notice when you start making derived generators, and then you make derived generators of derived generators and stuff like that, that it's not so convenient that everything is unfolded right away. Okay, because this yanking rule is something really about a cup and a cap. So I didn't really want to unfold my cup and my cap and everything straight away. So there's a keyword for this called def, which actually introduces a new generator called cup, and it introduces a new rule called cup def, which just lets me explicitly fold and unfold things by applying the rule. Okay, so let me change cup and cap to be those things. And now if I come back down here, let me just change this back to these things. Well, let me show you what it looks like with the rules. You notice this first rule works. Oh, actually, everything works. So one thing which would not work is if I just put fra here, because now it needs to know that it should unfold definitions. But one thing that the simp tactic does is it automatically unfolds definitions. Okay, so if I do simp unit L and now co-unit R, then I can get this in a single step. Okay. Also,
we probably just want to make it equals in, right?
equals, I think if I do this, yeah. And also if I have Yangar, which looks like this, that turned into a bit of a mess, of course, because probably these want to be right and left, not left and right. No, let's see what's going on here. Why am I stuck? Maybe Fro wants to be backwards. Yep, there we go. Okay, so interactive theorem proving, all about trial and error. Okay, so that's, you see, I've defined this Frobenius theory and I've started to prove some stuff about it. I can make another one. Let's say bialgebra. I think I won't write it. Let me just pull it from here. Let me put it here. Okay. So now I've done basically the same thing as I did for the Frobenius algebra thing. I imported a monoid and a comonoid. But now I've added the bialgebra equations rather than the Frobenius algebra equations. Okay, so there are these three rules. You notice there's a keyword called SW for swap. There's also a form of this called SW with a lot of stuff. This is a big swap, which takes an explicit permutation. Okay, so I almost never write these by hand, but it's pretty handy when you have, for instance, big terms like this with lots of swaps to not expand that as tons of pairwise crossings. Okay. Oh, this should have been called bialg, not demo. Bialg. Okay. Yep. Now, for my last trick, let me show how to put some of these things together. Okay, so far I've defined a purely hierarchical kind of theory where I've taken simpler things and I've loaded them in and added new rules on top. But if you know kind of how these diagrammatic theories go, you tend to kind of take more than one theory, like say 2 Frobenius algebras, and make them interact as a bialgebra. Okay, and that's something we can do in Chyp as well. So let me make a new theory. I'm going to call it IB for interacting bialgebras. Okay, this is also going to be pretty close to the phase-free fragment of the ZX calculus, if that's your jam. But nothing is commutative here, so that's an interesting thing, is you can actually get quite some mileage with non-commutative versions of everything. Okay, so let me again make some generators. Okay, but I'm going to make 2 copies now. And you notice I'm explicitly making my generators again, and you'll see in a minute why I'm doing this. B1. This should go 1 to 2. Okay, so here's a monoid and a comonoid. And now let's make another monoid and a comonoid. Okay. And now for reasons which are you know, completely clear to me, maybe to some people, I'm going to make one of these things green and one of them red. Okay, so this will start to look a little bit like ZX calculus. So optionally, you can just put a hex code for a color after these things to give it a background color. Okay, and that'll make things a little easier to see in a minute. So let's just make all 4 of these green. Okay, and you can tell which they are by their shape and by the label. And let's make all 4 of these red. Okay, so maybe I'll go EE9999 for people who may have limited color vision. Okay. So now we have a green set and a red set, or a light set and a dark set. You can't tell green from red. Now I can import, and I want to make one of these things a Frobenius algebra. Actually, I want to make both of them a Frobenius algebra. Okay, if I do import frob, well, If I do import frob again, then I get a whole bag of errors, right? Because everything's already defined. But I can actually explicitly give this thing a namespace. Okay, so I do import frob as f1, m equals m1, u equals u1, m equals n1, b equals v1. And then I'll do import frob as f2, m equals m2, u equals u2, n equals n2, v equals v2. And now I have two copies of a Frobenius algebra. Okay, and if I, for instance, if I look at, say, f1.fr, I get this rule. And if I look at f2.fr, I get the red rule. Okay, so now I realize I've just come at the half hour, but this is the last thing I want to show, is I can actually now import bialgebras crossways. Okay, so I'll do this. I'll call you B1 and B2 and import two copies of bialgebra. But now I'll assign my generators crossways. Let's see, I think I want to do it like this, okay? And you notice that all of my rules are now nicely namespaced. So if I look at b1.ba, I get the bialgebra of a green monoid crossing a red comonoid. And if I look at b2, I get a red monoid crossing a green monoid, okay? And then down here, I can start to develop basically the whole theory of interacting bialgebras and combining all the rules from these different theories and using different kinds of tactics and building up to all sorts of stuff. So I've been developing a theory of kind of quasi-triangular Hopf algebras and looking at how braidings and all these kinds of things behave. And yeah, so get the tool, play with it. I'll put the link back up here. There you go. And that's what I wanted to say. So thanks very much.
Okay, thank you. I think we have time for some questions out there. Dario.
Hi, Alex. Dario here. Two questions, one short one and one longer one. Short one is, you've shown support for props and prop rewriting, but what about more general symmetric monoidal categories with other generators? And the second one, kind of, where do you see this project going? Like, what are the applications for this? And are you thinking about using a larger meta language to actually write proofs in this, like Isabelle or OCaml or something?
All right, so lots of stuff. First, I think your first question was about props, which are single sorted, and whether I would go to multiple sorts. So like having multiple objects, different objects generating the SMC. Yes, definitely. I think that's a useful thing. Already with this example of looking at modules of a Hopf algebra, then you really want different types for that. So yeah, that's definitely somewhere this is going. Application-wise, I'm not sure. I think it was really, my idea is just to put the tool out there and see if people start to do cool stuff with it. And the third thing was about a richer logic. So I hadn't really thought about embedding this in a bigger theorem prover. I've tried projects like that in the past, and I found that the existing logic starts to get in your way somewhat because it doesn't kind of speak hypergraphs as a native language. So you kind of have to convince Koch what a hypergraph is and prove a whole bunch of theorems about it before you can even get started. But I think going beyond equational reasoning in this prover would be an interesting thing to do. So for instance, being able to prove like implications, like if I assume something, then I can show some other things. So adding like at least first order logic or something would be a very useful thing.
But the trick is, you don't do this in your language, you use a meta language for that. So essentially Chyp would be the kernel of a system where in that system you do the reasoning. And then, for example, you could try to prove completeness of graphic linear algebra or something, and this would be quite a nice project. We can talk about that offline.
Okay, yeah, that sounds cool.
I think there was a question online by Bob. Bob, if you want to unmute yourself.
I mean, the obvious question is like, is there a plan to have like a graphical interface and not a coding interface for this? Because it's about graphical reasoning. So why would you code?
That's a good question, and I was resisting a long time this kind of way of telling the computer about pictures. But for some things, it's actually faster. You just start to type things in parallel and in sequence, and it comes out very fast. So you can, I mean, you notice that I built a monoid, a comonoid, blah, blah, blah. I did all this, you know, in the space of 30 minutes. If I was drawing all these things with the mouse, it takes longer. But I think there is some scope for doing a kind of a hybrid thing, where you're sort of clicking and dragging some stuff, and also doing some code. But it's nice also that you have the proof document at the end. So you do all this work, and at the end you kind of have this document that is actually explaining the proof, and you could export this thing to LaTeX or something.
Okay, thanks. I do have another question, but if are there any other questions in the audience, Ed?
Thank you. At the beginning, in the motivation, you talked about how computing modulo equality for symmetric monoidal categories resulted in a sad emoji. So
Yeah.
I was just wondering, why is hypergraph isomorphism computationally easier?
Yeah, a couple of reasons. So for one thing, in practice, checking ISO of these things is not computationally very expensive, because all of your hyperedges are non-commutative. So a lot of the trouble you get into with graph ISO is where you have large amounts of sort of automorphisms of your graph. Here, there's basically, when two things are ISO, they're kind of only ISO in one way. Now, if we enrich this to be doing rewriting modulo Frobenius structure and stuff, that stops being true. But I mean, a more general thing is rewriting, even deciding if two terms are equivalent modulo in equational theory is a non-trivial problem. So, I mean, for some equational theories, this is even undecidable. So for SMCs, you can decide it, but in fact, the best decision procedure is just to compute the hypergraphs of these two things and check if they're isomorphic. And we have a whole kind of theory of confluence and critical pairs and termination and stuff developed for hypergraphs. So computationally, this has pretty nice properties.
Thank you.
I think we are going to leave for lunch now, but if you have any more questions, I think the Zulip chat is open for more questions. Thank you so much. I think we come back at 2. We have 1 hour and a half, so let's thank Aleks again. Thank you so much.
Thank you.
We'll be back at 2.